about proof singularity, I think that's get together pretty well, because I'm going to talk about proof singularity, and I'm going to talk about the viable paths to achieving that. Just a little bit by myself. I'm Shumo. I'm the founder of NEBRA Labs, and we have an amazing cryptographer from Cisco here who's chatting if you are care about the curves, finite field, and like a Chinese remainder theorem. So let's get started. So I think I don't have to convince this crowd, but just this first slide. I do think after 10 years, we have finally built the decentralized censorship resistance ledger, and it actually, the coolest part is actually support like coded settlement, which means it's Turing complete. I do think Ethereum will be our civilization's settlement layer, right? And I just like Google this picture here. Anyone know what's this picture? It's from Nordic myths. It's like I don't know how to pronounce it, but it's like a YGG Dressel, the word tree, right? The future of the digital civilization, I think it's kind of like this word tree, and this is Ethereum, right? And people are talking about like what's going next. Are we going to be like a L1, L2, L3, L4 to L infinity, right? I actually don't know, because maybe there are just like a lot of L2s, there will be AP stack and score stack, polygon stack, and there are going to be different kind of options. But there is one thing, it's pretty clear to me, is that a lot of these unique layers will be powered by zero-knowledge proofs. And not necessarily with zero knowledge, but powered by proofs. So it starts to emerging about like this, like all the promising primitives. They're actually all using ZK as a primitives to power one aspect or another of their protocols. So for example, I view layer 2s as horizontal scaling. By horizontal, I mean like we have EVM on layer 1, and we just replicate what exactly EVM do in layer 2. It's kind of like horizontal scaling. Like we have all these amazing like scrolls, if you think, Polygon, and Nimia. I know I have a different pronunciation, Nimia, who's like the last speaker, but I actually talked to the team. They themselves are confused by how should we. So I guess this doesn't matter. And we have all this kind of like privacy-preserving primitives. You can see like Somophore, Macy, they're all used by PSE. We have some like incoming private DeFi project. I think they are going to launch the mainnet pretty soon, Nocturne. And of course we have Aztec, who's using like privacy-preserving L2s. And the third category is kind of oracles, right? We have Axiom, Lagrange, it's the same type of oracle. Woo! It's mostly kind of it's mostly, to me, like ZK is kind of like glue, right? So basically, it's you using this like verifiable computation, you can glue it. I think Hamlet from Score, he talked about like, hey, like if something just like too much compute, just throw it to a snark, and then you can settle it, right? It's becoming kind of a universal like computing settlement primitives. You're going to settle on like blockchains, right? I think it's becoming like interesting and useful, and that's why people are thinking about like proof singularity, because the true like sort of the protocol design philosophy of proof singularity is that you just need to implementing this single like I wouldn't say it's simple, but it's just like a single primitive which is verifying zero-knowledge proof, and you are kind of pushing off the complexity to the edge. And as layer 1, as a base layer, you need some sort of kind of like simplicity, and you don't want to change the layer 1 code all the time. Kind of pushing the complexity to the edge, from my personal point of view, is a very, very good like a design philosophy. So then the question is, like, we're not there yet. I think one of the biggest problems today, in my view, is that the proof verification cost is very, very expensive, especially on L1. And here, this is a number. So it's actually depends on which kind of a proof system you are using. the kind of oldest proof system, Bor 16, has the least gas cost. So it's actually depend on the size of your pop input, and like 250K is kind of like a good average number. And if you think about that, under the assumption we have like a 20 GWA gas cost, which is actually quite moderate because the previous like past half a year's cost, even during the bear market, is kind of like a 26. And 2000 USD East price, I do think will be much higher. So it's $10, right? And sort of the second widely used proof system, like Halo 2 KZG, we're talking about like 400K gas cost, which translates roughly to like $16 per proof verification. And Stark, roughly you need about like 1.5 million gas cost, and it's like $60, like $60 for settle single proof. I think like Vitalik used to be famous said, do I want to pay $20 to add privacy for your transactions to buy a coffee? Probably just like once or twice, but this is not going to be sustainable. So that's why we're building like a proof of singularity with NEBRA. And we do have a very, very like long and progressive vision, but what our focus first is trying to reducing the proof verification cost and also scale the proof verification capabilities on this area. The simple question, right? How can we make ZK cheaper on chain? Right? Like how can we realize the magic? And our answer is we're using ZK, right? So we're using magic to achieve the magic. It's a hand-waving question, but it is, right? So this is the first primitive we're building. We call it the NEBRA UPA, standing for Universal Proof Aggregator. Let's go into it, right? So this is like a super high level idea what is a universal proof aggregator is, right? So we have the proof aggregator will not do the proving for you, right? You have to give us proof. So I think this is the best interface we can design because we can adapt to any kind of proving infrastructure. No matter you are a privacy preserving protocol, you need a client-side proof, so which is the zero-knowledge proof is generated by the client devices, or you are like a kind of a ZK infrastructure. You are using like a GPU-powered machines to generate proof, right? We just take proofs, and we call it universal because we can take proof from different circuits, which means no matter what kind of computation you are encoding, we can aggregate it. So then we take multiple proofs into single bundles in the NEBRA UPA, and we generate the aggregated proof. So this aggregated proof eventually is going to verify on Ethereum or deploy to L2s. And the cool part here is because the proof verification cost is roughly the same, right? Now instead of like verifying 6 proofs, we're actually verifying single proof. And more specifically, in our first generation of the proof aggregation engine, this is a Halo 2 KZG proof. So you can see the aggregation proof costs actually stay constant compared with no matter how many proofs we're aggregating per batches. And under practical settings, currently we're aggregating like a 32 proof per batch right now. That's like super high level picture of what we're building here. Oh, by the way, questions are welcome, and please interrupt if you,
Is this just one level of aggregation?
I will talk about that later. 5 slides ahead of that. Yeah.
How do you know the limit?
Sorry?
What's the limit of how much you can aggregate?
I think the practical answer is no limit. So, like, you can,
magic.
Yeah. Like, you can aggregate like 1 million proofs. That's totally doable. But there is a proof latency trade-off, right? And if you want, let's say, you aggregate 1 million proofs, you probably need to do like a multi-stage aggregation. and there are some recursion overheads, and there's some like latency trade-off here. I think the real proof singularity is where the last speaker was saying, right? So essentially, you can just have one proof per block on any protocol, and that could work.
When submitting the aggregated proof, you submit to your contract, right? So that means like your contract will have the right to update other rollups contract.
So we are purely in charge of verify. So
Yeah.
the contract endpoint deploy on various
But like
chains.
for now, each robot has their contract on layer 1, and when verifying the proof, they also update the state of their contract.
Yeah.
That means your contract can update their contract.
I guess like so first is that if you want to use us, right? So you need to use our contract interface, which means it's just standard interface verifying proof. You need to change your contract, but I don't think our contract has the ability to change their state because first of all, immutable. Secondly, unless we coded something wrong. Like
So basically, they need to integrate with your.
yeah. So people use us need to integrate with us, changing their smart contract. That's true.
This may be the wrong group for this, but outside of Ethereum, are there actual business marketplaces where there's people that actually want to pay for proofs?
Pay for proofs.
Like-
pay for proving things,
No,
or
like
pay for verifying things.
I have proofs I want to give to you, and you're someone who wants to pay for them. Outside of Ethereum, are there like actual, I think NEBRA is like an app ecosystem for proofs. Like who's buying proofs outside of Ethereum, or like who's using like the other? Like there's two sides, right? Like I can prove things to a protocol. There's someone who wants those proofs. Who is paying for those? Who's on the other side of that?
I think.
There's all these use cases like medical identity. But like, have you seen any use case? Maybe I'm out of sync with your presentation. I'm just curious.
Yeah, that's a very good question. So I think first is that there's a need of verifying proof outside the system for sure, right? But if you think about that, you need a consensus layer to sort of set the ground truth, right? Like the immediate question is like, hey, you have a proof, but who should you verify? In some scenario, if you don't need a ground truth, then whoever should checking the proof without checking whatever you're doing should verify the proof.
Well, I mean, this is a new paradigm shift, right? It went from like scraping data to now like users may be able to just like share their data. As people start to say, but like, who cares about like which orgs in the enterprise are actually going to switch to this model? If that makes sense.
Yeah, that's. I think. Yeah, it's first it's totally makes sense, and I think it's really about like who need a proof, who need to buy the proof, who need to verify proof. I think the answer is like who you need to convince, who you need to settle trust, right? That's why I mentioned Ethereum, in my view, will going to be the civilization settlement layer. You sort of have this ground truth layer, and every trust kind of grows from the root of the YGG drizzle, right? In some like specific use cases, maybe you don't need that, then that's fine. You just need to convince. You just prove to something that someone you need to convince. Then there could be some models there, and as a proof aggregation, as a protocol we're building on Ethereum, but we're actually open source. We're going to open source our toolings, and you feel free to use on your specific, for example, enterprise use case scenario. That's totally possible.
Yeah, is this similar to the original idea of the NEBRA? Like, so already have the and they have a fixed constant size.
I do think I'm not super familiar with Mina. So I'm not from Mina here. Can answer?
The idea was to aggregate the proofs.
Yeah, I think. I guess what we did a little bit different here is that we're actually able to actually proof from different circuit. You can express whatever you want.
What kind of proof system is it?
So, again, this is like a 6 slide before, but the currently we're internally on the Sequoia testnet. We can aggregate all kinds of gross safety proof.
Sorry?
Currently, we can aggregate all the gross safety proof, and we're building a universal aggregator to aggregate like all proof from different proof systems. Yeah, I will cover that in the future.
Is it using Slackware?
That's I'm happy to chat offline. The answer is no, and for a very good reason. The TLDR is that you need to put the GT, which is 12-degree extension field, in not just natively, but to put that into a circuit, and that probably give you like 1 trillion cell circuit, something like this, insane thing. So we're not doing that. Yeah. Great. Okay.
So for different circuits or different orders of these circuits, do we need a one-time setup or we need a different setup?
So currently, for example, it's not a problem for us. It's about your circuit, right? So for example, if your circuit you are using Grosset-King circuit, you do need trusted setup, right?
Yeah.
And then what you do is that I will talk about a little bit later, right? You need to upload your verification key to us.
Yes.
And if you are using something like Spark, then you don't, then you don't require it. Yeah.
But the system, like application itself, that's just within one task. Right?
Oh, we are not doing trusted setup because we are using the application system currently are building using like Halo 2. And for the next generation, we are thinking about using Spark 2. And neither of them need trusted setup. Yeah. All right, let's move on. So here this is a NEBRA protocol, right? So I just talked about the general idea of the proof replication word. And we are a protocol that deploy on Ethereum and L2s, right? So our protocol has 2 parts. First is a NEBRA UPA contract. And just a smart contract interface you can interact with us. We will have the same address among like Ethereum layer 1 and different L2s. And then we have an off-chain worker infrastructure. And we have a coordinator kind of listening to the L2 or L1 or L2 contract. And we have distributed provers. So these are the 3 high-level design goals of the protocol. First, it's permissionless. You can see the interface is contract, and anyone can submit a proof to us. And second is censorship resistance. I don't have a full detail here, but we are going to publish a censorship resistance mechanism design. In the very, very high level, it will be very similar to existing L2s. You have a box design. For example, we cannot even ourselves cannot censor your transactions, and there could be some like stake imposed. And third, also not least important one is that we want to support progressively decentralized proving architecture to a proving network. Yeah, I don't think we're doing that right now today, but once we actually very, very careful design the distributed system, it's very modular so that in the future it's going to be very easy to progressively decentralize. That's like 3 high-level design goals and the system infrastructures. There's definitely more effort behind this. So one thing I can talk about a little bit is that we actually build a scalable infrastructure in the sense that if there is more demand, we can actually immediately get more workers to join, so our throughput can be bigger. And if there's less demand, so we can use less workers and to keep the economy. So I think this is a key, right? So for example, maybe there is one day there's a lot of like ZK transactions on Ethereum. We want our infrastructure can be scalable with the demand. So that's a protocol. And the next question is how to use us, right? Like I previously noted, it's actually really, really simple. So one example is that when we first tried the first version of the internal testnet, one of our devs, he just like coded the Toronto cache example. Right? He just used 2 days to just like, including testing and getting everything working. Right? Actual coding time probably just like 2 hours. So, but from the high level, right? So on the left-hand side is how you verify the zero-knowledge proof today on Ethereum. You just deploy your verification contract, something like verifier.sol, and that one is calling some like a cryptographic primitive like pairing. Then that's it, right? And now we have a endpoint we call Saturn contract. So before you use it, you need to register your circuit by submitting your verification key, and then you just literally call the set and verify proof contract with your hashes of your verification key, your proofs, and public input, right? And that's it. So, which means it's very, very easy to integrate with your existing ZK application, either your application or layer 2. This is a little preview of the first version of the testnet product we're going to release, right? So we have 3 parts, right? The first part is the NEBRA contract. You can see we already get the contract verified. It's basically the endpoint. You can see we have an API called submit proof. You can submit proof to it, and this is the last version of the testnet, internal testnet. We aggregate a 27K proof already. The next thing is NEBRA SDK. Basically, it's a TypeScript SDK to help you to integrate NEBRA with your smart contract. And the next thing is a Proof Explorer, right? And this is building on top of the open sourced Shumo Explorer database from PSE. And basically, what happens here is that as a dev, right? So you want to know whether your proof getting included. We provide both API and proof explorer interface to let you know whether your proof has been included or not. That's sort of the product overview. So next, okay. Before here, any questions? Next, I'm going to a little bit highlight what happens behind the scene. Sorry, please.
Yeah, I was just curious. Can you go on the previous slide? Here you just say 32 verified proof and 2 rejected proofs.
Yeah.
What does that account for?
So this is a single bundle, right? So the single bundle will include the verified proof, but will exclude the rejected proof.
Okay.
Yeah.
So you're not aggregating them?
Yeah. In the final state of the aggregated statement will only contain spelling.
Okay.
So you can think of the aggregated proof as proof of proofs. Yeah, let's dive into a little bit in details of the technical part, right? So currently we are using 2+ layer of the Halo 2 aggregation, which means by default we are 2 layers. If we have more demand, we can expand. It's really due to the current kind of inefficiency of the Halo 2 cases recursion overhead. And the major technique here is that we need to do a lot of non-native arithmetics. So I'm talking about the Chinese remainder theorem. This is not a joke, actually. Basically, we need to code this kind of a field simulation circuit using the rough idea is using the Chinese remainders theorem-based field simulation with lookups. And the author is here, actually. Yes, if you want to nerding out the circuit construction details, you can ask Francisco. And on the back end, right, so we have a pipeline and a distribution proving serving architecture, which means so basically it's triggers by the proof submitted on chain, and we actually chop into the bigger batches into smaller batches, so that once the smaller batches has been fulfilled, they're already starting the aggregation, and we also overlapping different batches as well. So for example, once the aggregation server is working and there's some incoming proofs, the next cluster aggregation service will be working as well. It's fully pipeline. And last but not least, we're actually using GPU acceleration to get better latency. So in the sense that from the technical point of view, there are 2 important metrics. One is throughput. So our throughput basically can fully be scaled by the demand. Now the real limit is how much proofs we can put in a single Ethereum blocks. And for the latency, so roughly we get 1 to 2 minutes prover latency. But your kind of transactions need to hang out in the mempool pools a little bit, at least in the Ethereum L1. I think in L2s, this kind of command pool latency is much less. That's a 1.0. And 2.0 is by the way, the 1.0 we will have a testnet pretty soon. The NEBRA UPA 2.0, we will try to address problems that in the 1.0 we can only aggregate Gorsic team proof. So instead, we're actually building a proof aggregation VM, in the sense that we want to have a generic proof aggregation VM that supports all kinds of proof systems, and also, more importantly, being able to support the future proof systems incoming. Because the constant pain working in the zero-knowledge proof area is that the cryptographers, they are working too hard, and they're building newer and better proof systems over time, so it's kind of moving target. And the idea of proof aggregation VM here is that a single VM instruction, a single VM execution is a single proof verification. And we can potentially using the faster recursion techniques. It could be folding, could be like a smaller field start based continuation to kind of like fold the VM executions so that we have a much powerful primitives to aggregate even more heterogeneous proofs. And there are some key ideas here we're exploring right now. So first is that using second curves for even less non-native arithmetics is kind of a little bit similar to like Aztec's gobbling plunk idea. And the second idea is that exploring more efficient polynomial convenience schemes and designed and optimized for like recursion overhead, and lastly more efficient lookups. So that's sort of the technical deep dive we're happening under the hood. Last but not least, I want to talk about some more interesting use cases just beyond just making the proof cheaper, as we call universal proof composition, right? Think about you want to entering a light club at Zuzaloo in 2030, right? You probably need different kind of proofs, right? So first you need a proof of humanity, not necessarily from WorldCoin, but maybe from somewhere else, to prove you are human. But maybe we need to have a robot-friendly clubs. But I just picking a particular scenario. You probably want to have a storage proof. You are holding this ZooPass NFT, and you need to have a proof of exclusion on the forbidden list. For example, all the club will ban some like assholes, so you need to prove that you are not. So, but you need to aggregate that proof, these proofs, atomically into a single statement, and we can actually just do that from day one because we support universal proof aggregation. And there could be more interesting use cases to sort of aggregate the composing different vertical vendors and ZK startups. We can build in more powerful applications here. Yeah, last but not least, we're hugely inspired by this proof singularity vision proposed by Vitalik. And I do think looking even longer term forward, there possibly for every useful protocol being built, there could be a debate on to be enshrined or not enshrined, and like, well, any like L2 protocols interested to integrate proof aggregation natively in their protocol. We're happy to talk about that. So this is a team effort. Like I said, Francisco is here. There are many other folks, and we get a lot of help from great cryptographers and also ZeroXSparks community here. I would like to take any further questions.
Slide you mentioned this notion of proof aggregation VM instead of proof aggregation secret.
Yeah.
Can you elaborate a little bit more that what are the basic operations of this VM? Like?
Yeah, so VM, so like, I guess first like why you need the VM, right? Because thinking there are if you view the future is there are going to be many proof systems. Like we don't want to just write a circuit for each proof system. That was just too much for us to handle. But if you're just using an existing VM, for example, like RISC-0, you'll be very efficient to handle this like a cryptographic like specific primitives. So our VM is more like a chiplet. So we're going to code cryptographic primitives, for example, in curve operations, hashings. This like widely used as kind of like a circuit, right? We're using going to use like a memory argument to sort of hook these kind of many chips together. And then on top of that, building a DSL to specify. And more specifically, right, if you think about different proof systems, like people using like kind of different numbers for passes for Fiat Shamir, this kind of thing need to be more flexible. It doesn't make sense to build a single circuit for each of them. And then after we have Fiat, just have a very minimal DSL to express the proof verification as sort of the DSL of this. And then you can using the fast recursion techniques, either continuation or folding, to kind of aggregate this single proof verification process. I'm sorry.
I think this necessarily won't be an issue for a while, but I'm curious if you've thought of prover collusion attack, if you've thought through prover collusion attacks at all.
Can you be more specific?
Yeah, like a scenario where so I don't know how the tasks are delegated to the provers, so that maybe is part of my question. But
so I think I guess maybe I can do a little bit clarification first, right? So what prover can do and cannot do, right? So what prover can do is the prover cannot include your proofs in a single batch. That's the only bad thing the prover can do, basically. So basically, the prover cannot submit a malicious proof because we are immutable systems, and because unless you break in the cryptographic primitives, right? So which actually gives the prover less attacking primitives. The real tricky thing actually happens is because everything is at EB. If the proof, the effect of the proof will end up into some DeFi transactions. For example, we're talking about talking to Nocturne, private DeFi protocols. Z-Warrior or some of the MEV scenarios, basically, if the prover has some powers of not including your transactions or see your transactions, getting some metadata from the proof, despite by construction it's impossible because of ZK, right? But maybe there's some public data, public input. You get some metadata. Then theoretically you may have some front running opportunities. But this is kind of a long tail risk. We probably won't deal with that right now.
Yeah, I can catch up upstairs.